Now, we're only doing section 12.4, but this comes from section 12.5, where after we've come up with all these rules for finding the limits as n approaches infinity, we do actually follow all the way through with the process to find the area underneath the curve. I don't recall this being done in calculus. I mean, I know that finding derivatives by doing the limit of the difference quotient, yeah, you're going to do that probably many, many, many times. I'm not sure that they actually have you do this. But I still find it kind of interesting because it does tie together other things that we've done in the class. That's why I kind of like to do it. And so I'm just going to show it. That's it. But in this problem here, we are trying to find the area underneath the curve of f of x equals x squared between x equals 0 and x equals 1. Between this is the A and this is the B. Right? Okay. So here's the curve. X, here's our A. Quiet, please. There's the A, and there's the B. We're trying to find this area. Okay. So we're using the same limit, right? I equals 1 to n, and they've reversed the order of it, but here's your width of the rectangles, b minus a over n. Here's the height of the rectangles, f of a plus b minus a over n, which is 1 width, times I. And because you can actually substitute for the b minus a, we know the b is 1 and a is 0. So that makes everything simplify down to this here. In fact, we can get to this point right here. We have the sum is I equals 1 to n of I squared over n to the third. And the thing is, that n is just whatever number's on top of your summation. It's actually not changing as I increases. N doesn't change. It's a constant. So that can be pulled. The n to the third comes outside. So now we've got 1 over n to the third times the sum, I equals 1 to n of I squared. Okay. Back in chapter 9, when we were doing math inductions, we were proving things like this. We were showing that this formula right here, the sum of the I squareds, is like saying 1 plus 4 plus 9 plus dot, 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 plus n squared equals, and we had a formula for the S sub n, which was this right here, n times n plus 1 times 2n plus 1 over 6. So remember, this was our A sub n, this was our S sub n, and we had to show that, first, the formula works for n equals 1. Second, if you assumed it worked for n, that it must work for n plus 1. So then, just like dominoes, since it does work for 1, it must work for 2. And if it works for 2, it must work for 3, and so on to infinity. We proved that formula back in chapter 9. So at this point, when I've got this, I can use that, a formula that we've already shown to be true earlier in the class. And so we end up getting this, which is like that last example that we did where, yeah, there's some complicated stuff going. It's actually the same thing inside the brackets this time as it was in that example. And they actually multiplied it all out, but they didn't really have to because the only thing that mattered was the highest degree term, right? We have the 1 over n to the third and the 6 in the denominator. You got the 2n times n. So we end up with 2n squared, 2n to the third over 6n to the third. And you take the limit and you get 2 over 6, 1/3. So the area under the curve between 0 and 1 is 1/3. If you were doing it with calculus, you'd do like this. You'd set an integral. You'd say the integral from 0 to 1 of x squared dx. And you'd increase the exponent by 1, divide by that exponent, and then you'd evaluate from at 1, and you'd subtract what you get when you plug in 0. So what do you get when you plug in a 1 to this? 1/3. And then you subtract what you get when you plug in 0, which is 0. So the answer is 1/3. So, like I said, I'm not sure that you would actually be asked to go through this whole process in calculus, like you would for a derivative, have to do the limit of a difference quotient, but that's what's behind an integral. You'll remember it next year if that's